Hi guys, today we're going to be talking about natural logs and their integrals, and that is in chapter 5, section 2 of your textbook. So first off, let's talk about what actually is, how do we actually use natural logs in integration, and from the previous section we know that the derivative of a natural log is 1 over x, or dx over x. So using that logic, we can say that the other way around, that the integral of 1 over x dx equals the natural log of absolute value of x plus c. And it's absolute value because it can be, with an integral you have a lot of variance. And just the same, the natural log, or sorry, the integral of 1 over u du equals natural log of u plus c. And that means u being any function that you may encounter in that form specifically. So first we're going to start with a simple problem using u sub, which will have the definite integral of 1 to 3 of x over x squared plus 1 dx. So with u sub, you always want to let u, just as we saw in that base formula, we always want to let u equal the denominator, so u equals x squared plus 1. So du would be 2x dx, dx would be du over 2x. And then we also have to evaluate u at the limits. So u of 1 is 2 and u of 3 is 10. And so now we're going to rewrite this integral. So it becomes the integral from 2 to 10 of x over u, and then we have that 2x down there, du. And then the x's are going to cancel out, and you can put this 1/2 outside of the equation, so that becomes 1/2 of the integral from 2 to 10 of du over u, which just equals, and using that base formula, we can now say that this is 1/2 times the natural log of 10, well, absolute value 10, minus natural log absolute value of 2, and you can just leave it like that. So sometimes the function is not going to look quite like what you need it to be looking like to use natural log whenever you're integrating. So let's look at the integral of x cubed minus 6x minus 20 all over x plus 5 and dx. So what you're going to need to do here is use long division, or what I use is the this form. So you make this -5 because you said x plus 5 equals 0. And then we're going to have the coefficient of each one. So we'll have 1 for x cubed, 0 for x squared, minus 6 for x minus 20. And then we're going to, so we got -5. And we're going to multiply -5 times -5, which gives you 25. Oops, excuse me. -5, and you get -4, and then you get 20. 20, -100, -106, and then 5, So negative 5 times that is 530. So it's 510. So that essentially comes out to negative 4x squared plus 20x minus 106 plus 510, and then you're going to make it over the denominator, over x plus 5. And then, so this is what our new integral is. And so since these are all separate, you can essentially separate out the integrals. I'm not going to do that because there's not enough room, but they can separate each integral because it's a plus and minus. So the integral of negative 4x squared equals negative 4x cubed over 3. So let's write that. And then there's going to be plus c because it's indefinite. 20x is 20x squared over 2, which is just 10x squared. And then 106 is just negative 106x. Then 510 over x plus 5 is where you get your log from. So you can just take 510 out and make that 1 over x plus 5, because then you get that in natural log form. So that just equals 510 times the natural log of x plus 5 plus c. And then, so we'll just bring that down there. So 510 times natural log of x plus 5, and then plus c. And that's your answer. So sometimes it's complicated, sometimes it becomes a nice equation in the end, just depending on what you get. So we've done long division with natural log integration, and we've done u sub, but now there's another way of using natural log, which is the trig function integrals. And because some of the trig function integrals, well, actually every one of them except for sine and cosine, have integrals that include the natural log, and we can use trig identities to do that. So we're going to take a look at how we derive the integral of cotangent x. So first off, we're going to write the indefinite integral of cotangent x dx. So we're going to use trig identity, and so that equals the integral of cosine x over sine x dx, because cotangent is cosine over sine. So we're going to let you always let u equal the denominator, because we're going to use u sub, we have to. So u equals sine x, du equals cosine x dx. And so dx equals du over cosine x. So we're just going to plug this into the integral. So it becomes cosine x du, sine is u, and there's a cosine x in the denominator, and those cancel out. And so then it just becomes the integral of du over u, which equals natural log of u, well, absolute value of u plus c. And that comes, once you plug in u is sine x, that just becomes natural log of sine x, absolute value, plus c. And that's how you derive that. That's how you get from this to this. You can also take a look at using the other way around, which would be tangent x. And so the integral of tangent x dx equals integral of sine over cosine, sine x cosine x dx. U equals cosine x because it's in the denominator now. Du equals sine x dx, negative sine x, sorry, dx. So dx equals negative sine, or negative du over sine x. So plugging that all in, you have, put the negative on the outside, sine x, cosine is u, there's a sine x in the denominator, and you have du. They cancel out, that equals negative du, or integral of du over u, which equals negative natural log absolute value u plus c, which equals negative natural log u is cosine x plus c. And that's how you derive the tangent integral. So let's look at a few more natural log problems, or problems involving natural log and integrals in general. So say you have 4 to the natural log x over x, or the integral of 4 to the natural log of x over x dx. So this may look complicated because in this sense you cannot use u sub in the denominator because that won't work. So what you want to do is get u equal to natural log, because you don't want that natural log in there as far as integrating it right now. So du equals dx over x. And you're going to see that this comes out quite nicely because you already have dx over x right there. So you don't need to do anything else except for make this the integral of 4 to u of du, because du equals dx over x. And that just equals 4 to the u plus 1 over u plus 1 plus c. And plugging everything back in, you get 4 to the natural log x plus 1 over natural log x plus 1 plus c. So there, you also might want to do the relationship between e and natural log of x whenever it comes to integrals. So we're going to have a definite integral of 0 to natural log of 3 of e to the negative 2x dx. Let u equal negative 2x in this case, because we want e to the u. d to the u equals negative 2 dx. So dx equals negative 1/2 times du. So plugging this in, and we also need to evaluate at the limits. 0, 0 is 0. U of natural log of 3 is negative 2 natural log of 3. And so evaluating at the integrals, you have negative 1/2, 0 to negative 2 natural log of 3, e to the negative 2x dx, or sorry, e to the 0, e to the u du. Don't want to forget about that. So this is going from more like a to b because, sorry, this is going in the opposite direction. It's going from positive to negative, so we need to switch that around, which will give you the negative integral. So that negative cancels out, so we can just make this 1/2, and we're switching the limits around because we need to go from lesser to bigger. So it becomes negative 2 natural log of 3 to 0 of eu du, which is just eu, because derivative and integral of eu is the same. So it's equals 1/2 times e to the 0 minus e to the negative 2 natural log of 3, which is just 3 to the negative 2, or the natural log of such, which is the natural log of 1/9. And so e to the 0 is 1, e to the natural log of 1/9 is just 1/9, because those e to the natural log cancels out. So 1 minus 1/9, 1/2, so it's 9/9 minus 1/9, so it's 8/9. 1/2 times 8/9 equals 8 over 18. And then that's your answer. And so you always want to get a relationship between, whenever you're doing integrals with natural log and e, to where you can get everything to cancel out, especially indefinite integrals, because that would most likely be the purpose of such integral. In the words of the Frosted Tip legend himself and his band NSYNC, bye bye bye. See you guys next time. Study 5.2.